So part C also asked you, is this approximation less than or greater than the true value? Explain your answer. So if you look at Q, 10, 7, 4, 3, 2, 1, this is a decreasing function. If I have a decreasing function, it doesn't matter if it's concave up like a cup or down like a frown, a left Riemann sum, this is an over approximation. Because VQ of t is decreasing. And we used left endpoints to approximate. So I've used a lot of paper here, so I'm going to go ahead and just write problem 1. And I'm going to go ahead and do D. Now, part D says, is it true that particle Q meets particle R on some time between 7 and 10? Explain your answer. So I need to know for Q, what is the position X Q of 7 or like, and XQ of 10. I also need to know XR of 7 and XR of 10. So to know if they're going to meet, right? Do the two particles meet? Are they going to have the same position somewhere between 7 and 10? So, well, good news is I found XQ of 10 in part C. So this is 66. And I'm going to need XQ of 7. Now, this was the biggest it could possibly be, so I'm going to try and find out what the smallest it could possibly be on this side. So, because this was just an estimate. So, because left-handed approximation gave me the greater approximation, I'm going to do a right approximation to find X of 7, X of Q of 7. Now, so what I'm going to do is XQ of 7 is equal to XQ of 0 plus the integral from 0 to 7 of velocity of Q of t again, dt. This was an over approximation, so it's giving me the biggest thing on the right hand. I want the smallest thing on the left hand side. So this is going to be XQ of 7 equals, this XQ of 0 was 9 plus, and if I'm going from 0 to 7, if I'm going from 0 to 7, I don't have 5 rectangles, I have 4. So this has a width of 3. And now I'm not going up the left side, I'm going to go up the right side. So that's going to be 7. Plus 2 times 4 plus 1 times 3 plus 1 times 2. So this is going to give me an under approximation for 7 because I used right endpoints. So this is going to give me XQ of 7 equals, plug it in, plug it in, plug it in. So this is 43. So my values from my position from 7 to 10 is 43 to 66, with this being the very smallest and this being the very biggest. This is an underestimate. This is an overestimate. Now, how do I find position for R? This is acceleration from 7 to 10. Well, I do know the equation of this line. From 7 to 10, this is the line acceleration of t equals, this is just the line y equals 2. So my acceleration at time equals, acceleration of t from 7 to 10 is just 2. So let's integrate it. So this is going to give me my velocity is 2t plus c. Now, I can figure out what c is because I know velocity at time equals 7 is 4. So my velocity is 4 when my time is 7. So 4 is equal to 14 plus c. So c is equal to -10. So now I have a velocity function. My velocity at time t is 2t minus 10. Trying to get to position. Well, integrate. My position is equal to 2t squared over 2, so t squared minus 10t plus c. Oop, but I'm calling position x, sorry. X of r. This is of r. So if I know my position function, but I know my position at 7 is 20, my position at 7 is 20 equals, at time equals 7 is 49 minus 70 plus c. I got a calculator, right? So my position is, or my c is 41. So this means that my x r of t is t squared minus 10t plus 41. So here I knew my position at 7 was 43 and my position at 10 was 66. So can I find my position here? So here and here. So I'm going to put a of r of t was equal to 2. So I integrated. So actually know my position at 7, they told me. My position at time equals 7 was 4. Can I find my position at 10? Well, I have a position function here. So my position for r at time equals 10 is 100 minus 100 plus 41 is 41. So particle r is between 4 and 41 from 7 to 10, and q is between 43 and 66. Is there any time that they could meet? No. Particle q and r will not meet on 7 is less than t is less than 10 because q is between 43 and 66. And R is between 4 and 41.